experiment with my current load tester, which is this. I have to mention that this circuit is actually without this resistor and without that transistor to be a tester. You have to change them and adapt whatever transistor you want to test, and in accordance to put its proper load resistor, like I did here. Remember when I had all this beautiful animal that I'm having here? You know, it's too powerful, and you don't need, for certain experiments, for certain transistors, you don't need that powerful resistor. So you have to adapt the load resistor. And let's look on the circuit diagram. This is the transistor that is there, and this is the load resistor, which is this. And of course, this data is not, at least this 0.25 watts is not correct for this circuit that I'm having here. So this is an X load resistor, and this is an X transistor, whatever you have to test there, and in accordance to change this in respect to that. So that's the only detail, the only idea that I had. And I'm keeping this circuit for a few days actually on my table, and I tested this guy here. This is the BC548, and it is absolutely fine. It's working absolutely completely correct. It is not damaged in any way. As you can see, it's functional. It was saying on this large heatsink here, if you remember. But here I tested another heatsink. It's a simple piece of aluminum, which it was like this in this C shape, and I bend it like that. And this is a scrapped aluminum radiator from somewhere. So now what I'm having here, I'm keeping the diagram here for a quick look over it. But remember, this value and this value are changed now from the original circuit that I had. The rest of the circuit is absolutely the same, including that one resistor, but this resistor are changed. So that's the difference now in this setup. So now I'm using this BC. Let me put it here, because that's the transistor actually there. Is from here to there. That's it. That's the transistor. It's this little guy is here. So it's a scrapped transistor. It's not a brand new one. So this is a BC174. What I put my hands on. As you can see, they're all together. All those are scrapped, including this one. So this one that I'm having here is a BC546. That's the name of it, and is an NPN, 30 volts, 100 milliamps at 500 milliwatts. So this is the maximum wattage that you can drive it. Well, that is specified in its datasheet, 500 milliwatts. But here in my setup, the things are a bit more higher than that. So you will see how I'm calculating the thing and how I'm extracting all the data that I need. So right now I'm having 5 volts there with 500 milliamps. Yes, 0.5 amps. This amperage that I'm seeing here, I'm setting it from this potentiometer. Okay, so when I'm changing the potentiometer, I'm actually looking there and I'm looking at what current this entire circuit is drawing. So right now is 5 times 0.5. It means 5 volts times 0.5 equal 2.5 watts, the entire circuit, all these things here. So this is 2.5. As you can see here, I noted it, 2.5 at 40 degrees Celsius. And I measured it very close to it. And unfortunately, it is getting very slowly to this temperature, but is increasing, but very, very slowly. Probably 10, 15 minutes like that. Because this transistor that I'm having here is the area of it is very small probably. And it takes time for all this aluminum to sink. The dissipation is very, very slowly dissipation. Comparative with this larger one, that it was a little bit more faster. So that's the thing. If you leave it long enough, it will get to this temperature. So now all this circuit that I'm having here is at this wattage. But now let's see the real wattage on this transistor and the real wattage on this resistor. And I'm keeping my finger on it. And as you can see, I can actually hold it there because it's warm towards hot, but I can support that kind of hot. It's not that hot that you retract your finger from it. So it's manageable. It's a hot resistor, but it's manageable. And this one here, I'm actually putting my finger on it, and it's quite, yeah, this is hot. And I have a thick skin, and I cannot sense it that well. But it is hot. If I'm keeping my finger too much on it, it's becoming unbearable. So here in the center, but here is radiated, the temperature. And let me ensemble my phone holder here. Let's do some measurements, because this is the most interesting part. So now is on voltage set. Okay. So all that I need is, I'm having it mention it here. Q2 is this one, which is that. Voltage on collector emitter, which it means on here and here. So collector and emitter, I'm getting the voltage over it. Then R1 wattage, which is this guy here, and I'm getting the voltage over it. So let's do it step by step. So on collector and emitter, you cannot see the C there, but this is the base, collector and emitter. This is the arrangement that I'm having there. And emitter here and collector. So it's 4.45. So voltage collector emitter equal 4.45. So this means the current of 0.5, which I'm taking it from there, so 0.5. So the wattage over that transistor is 4.45 times 0.5 equal 2.2 watts. And let's see over this resistor, so this is for the transistor here, 0.4.9 or 0.5, okay, 0.5. So R1 voltage equal 0.5 volts, and current is the same, equal 0.5 amps, and the watts equal 0.5 times 0.5. 0.5 times 0.5 equal 0.25 watts on the resistor. So this is the maximum the resistor is actually built. I was getting lucky with this value here, but I was using a larger, thicker resistor here initially. And I can show you. I built it like this. It's 0.47, each of it at 2 watts. And it's from here to here to here to here. So it's in series. So in total, it means 1 ohm, 0.9 or 0.94. So very close to 1 ohm resistor, 1 ohm at 2 watts because it's in series. So, or probably a little bit more than 2 watts. And I had this guy here, which is pretty big, you know. And when I calculated the voltage, like I did here, I realized I have 0.25 watts. So I immediately changed it with a normal, the usual resistor, which is at 250 milliwatts, is what I'm having there, exactly at the limit. And it's not that hot. It is hot. It's probably 40 degrees. I can use my thermometer. So right now in my room, 26. So you see it's 25, 26 right now. So let's see the temperature over this resistor here. And I'm telling you, it's not that hot to the touch. So it's rising up to 47. And probably, if I'm moving it around, 48 here. Yeah, 48.5. So it's less than 50 degrees Celsius. So it's starting to slow down here. It's somewhere around 48. Okay, so it's less than 50 degrees Celsius. It's manageable when I'm putting my hands on it. And this is the maximum. This resistor is the maximum wattage that it was built to work at. And let's see the transistor here. I really don't like this probe. I have to find another probe that is. This is very easy to break it, like I'm using it. This is not supposed to be used like this, like I'm using it here, but it's the only thing that I have. Yeah, this is 50 here. Well, in my other experiments, probably that 40 was, probably it's from somewhere here. Probably I took the reading here, not that close to the transistor. That's why I put that 40, because I took the measurement a little bit away from it. But if I'm going into it, very, very close to it, and getting that 50 degrees Celsius, which is okay. But it's manageable. Now, it matters how hard it is pressed here as well, because it will dissipate the temperature a bit more better. It's not that I'm using excessive force. It's just a little bit more harder, and that's it. Because, and this is very important, this is aluminum, and it will eat the threads in the aluminum if you are pressing too hard. So you have to use force, but not excessive, because you will damage the threads in the aluminum and sayonara. And you kind of balance it, you know. So this is my experiment that I wanted to show you, that this transistor, which is rated at 500 milliwatts, I'm actually, right now, I'm driving it 4 times its rating. So it's 500 milliwatts, this is 2.2 watts, and it's more than 4 times. It's 4.05 times. What I realized with my previous experiment when I used this two, this transistor bigger and this resistor, and when I'm using now this transistor and this resistor here, what I realized, that's why it's good to take a little bit of time and stay on your circuit a couple of days. And even if I have absolutely no idea how to use the best potential from this circuit that I'm having here, just looking at it, not playing, not doing anything, just having it here on my table and looking at it and poking it. I took the measurements once and that's it. And after that, I was just simply looking at it and thinking about it. I didn't know what to do with it to make it a single basic circuit, because it's having this these external components that you can switch this resistor and that transistor. And also from the collector of this transistor, you can attach something else here on this. Instead of being attached to the power supply here with this wire, you can attach another component that is powered from the same power supply from here. So the power will go through that component and test that component instead of this transistor and this resistor. So it's a little bit more complex. You can do a lot of stuff with this circuit, and I realized it by leaving it here and looking and thinking of it. I realized this potential that you can do a lot of things. And one most important thing you can do, other than testing transistors, is that you can test also heatsink, aluminum heatsinks or copper heatsinks, whatever is sinking the heat from your component. Doesn't matter if it's aluminum or now it's warm to hot, and it's complete, it's entire. So now it took a lot of time. All this time, even before when I started the movie, I started the circuit, because now it's the proper time to get the temperature. So you see 25.6. It's a bit more warm, 54, 55. So I'll have to change that 40 degrees there, because it's not that relevant. Yeah, you see here a little bit further from it is 40, and that's what I was reading there when I took it from here. You know, it's not correct. The correct thing is to take it from the very close to the thing, to 55, 56 even. Oh, 57. The thing is that this radiator is heating up in time, and as long as it's heating up completely, the entire material that is having even on this side, when it's becoming completely uniformly heated up, then this radiator temperature is the proper temperature, when it's uniformly heated up, and it will get uniform, but in time. You have to let it cook, like the transistor that you're testing there. You have to let it cook for a couple of minutes, 10, 15, 20 minutes even, depending how small the transistor or the surface of the transistor is. I didn't use any thermic paste. It's just the transistor and the material here. The thermic paste probably will help dissipate the temperature, make the contact a little bit better, make it heat it up more quickly than it is right now. That's the thing. But other than that, it's perfectly fine as it is, like this as well. This is the video about what I wanted to make this video, and this experiment actually. I wanted to test if I can get over the optimal power suggestion that is written in its datasheet, and you can. So 4 times over that. So wow. It's not convenient to use it at this power, at this higher power here, 2.2 watts, because the size of the radiator that you have to use. But it is possible to use it at this power. Not everything in the datasheet is fixed you can go over it and you can go around it if you know how and if you are careful, because I am very careful. I don't want to burn any component that I'm having, neither the resistors, neither the transistors. I was actually thinking very seriously about it to use a heatsink for the resistors for the load. This is a load resistor that I'm using here. So to use a little bit of heatsink from aluminum or something that is forming over this shape of this resistor, not only a few points there and there and that's it, a few contact points, just to emulating like that, so to have something and not to make any kind of shorts. That's very important. And I was thinking about this situation. It's a very interesting circuit. It's a very interesting tester, current load tester. For now, at the moment, I'm using it only to test the wattage, the power in transistors, which I'm putting it here with this with the collector linked to the power rail here. But I'm planning to test other components in series with this transistor, with this power transistor here, and test their wattage. And this power transistor that I'm having here, its wattage that I'm having on it, not to be a concern anymore. So in this respect, in this idea, I purchased already a few more powerful transistors than this. This is a shit. My friend from America was using another transistor way more powerful than what I'm having here, and not needing such big heatsink like I'm having here. This is occupying a lot of space, and that powerful transistor that he is using was at 110 watts or something, and this is rated only to 40 watts in comparison to that one. So the conclusion that I get from his experiment, and he showed me the pictures, he showed me it's exactly this circuit diagram that I'm having here. Instead, he put here a 2 kilo resistor instead of this direct link that I'm having there. That was the discussion with that guy, that he was using a bigger transistor, and I'm using this shit. This is a shitty transistor, what I'm having here, that necessitates a bigger heatsink, extremely big. And also this one is even shittier than this, and I cannot raise it at too much power because it will probably burn up, or I will need a even bigger heatsink like this. And that's a space problem. It's too much space occupying only to drive at a higher wattage a little shit of a component, of a transistor. So that's a problem. And the solution that I observed in his experiment, in his board, is that he is having more powerful transistor, and in the same time, it means that that transistor is a better transistor than this shitty transistor that I'm using here. So my transistor is shitty, his transistor is better. So that's the conclusion that I draw from this talking with him. And then I got to the conclusion, well, I have to get, I must have some better transistors that are more powerful and can support more stress, more thermical stress than these shitty ones that I'm having here. And I already commanded a couple of them at $5. I will get 10 of them. Unfortunately, they are quite expensive for my capitalistic Romanian pocket. It's already too expensive experimentation that I'm doing here, but I wanted it to make it. That's what it will come next. I will get those transistors, those powerful transistors, and only one I will use, and I will use it here as a load transistor instead of this. And that powerful transistor will not need. That's the idea why it is better than this shit that I'm having here, because that powerful transistor that he showed me on his board there in America was not needing any kind of heatsink. So the construction of that transistor internally there, the power management inside that transistor is way better than what this can manage at a certain power. That's the difference. So this will heat up very high temperature and very quickly, and that will heat up not very high and not quickly like this. It's important how high is getting to a certain temperature. That's the problem. And this is way too high temperature, and it needs bigger heatsink. So that's the problem. And bigger transistor for powerful stuff like here to use. And why I need a transistor is that I will not care anymore about heating up this transistor, because so in the same time I have to customize the resistor value and size with the transistor that I'm testing usually. But when I will that powerful transistor instead of this one, it will be by itself without overheating like crazy, like this one was overheating and necessitating a lot of heatsink here. By itself, it will resist to a lot of heating. Theoretically, from what I understood from my discussion with my friend, I hope he was not lying to me. And then I will adapt the load resistor here in accordance with that power transistor, and the circuit will be complete from the perspective of putting other components and testing other components with this variable circuit that I'm having here, and complete with the power resistor here. And that's the idea. This is the idea, to test other components with this, because until now I didn't had powerful transistors to drive something else through them, because this transistor was blowing up pretty much. And I observed that I didn't let anything to blow up. I only made one mistake, but that doesn't count. So my intention is not to blow up anything, and to actually be able to variably control this transistor load and power over it, and not to blow it up and not be a problem. But until those powerful transistors will arrive, and it will take 1 month, probably 2 months even, because here is Romania and everything is possible. And you don't have to expect two miracles like 1 month. And until that time, I plan to test some SMD transistor instead of this. So I will have to make a special setup, a special way of wiring. And as you can see here with through hole pins, longer pins, is relatively quite easy to isolate them from each other and from the aluminum conductive element that I'm having here with these tubes that I'm inserting them on their pins, which are dangling around. They are not mulated. They are not strongly, pressed on the wires or on the pin. They are moving around very quickly, actually. But doesn't matter. They are doing the job of staying put there, and it's a little bit of force probably keeping them there all together here. But if you are fucking around too much with this device, they will fall away. So that's my next idea to test a SMD transistor and to overpower it like this, like I'm overpowering this transistor right here. It's not much. This wattage is not that much of a wattage, but in general speaking. But for this specific transistor, it is a lot. It is 4 times over its rating. So this is quite glorious, for him. For him, it's a glorious transistor right now. Yeah, it's pretty hot right now, and I reached 44 minutes, probably 50. I leave it warm up before I started the video. So after 50 minutes of running, so almost 1 hour. Let's see now the temperature over it. So around it a little bit, yeah, it's a little bit higher here. It's 43, 44 here on the margin. Oh, 45. Okay, and next to it is yeah, 53 is not that much. It's good. It's good. I was 55. I was expecting 60. 55, 56, almost 60. Yeah, 56. Okay. All right. Well, it's not okay, but this should have been written here instead of those 40. So 50, 56. If you are not running it too much time, like I'm running it right now for testing, 50 minutes of testing right now. So right now, let me actually write it there. 56 degrees Celsius, 50 minutes. Okay, so this is the conclusion here. So that's this is not that correct here, this 40 degrees. It is correct for a couple of minutes, probably probably less than 5 minutes. I should mention this as well. So less than 5 minutes. Okay, for that 40 degrees, it's fine if you're running it from time to time, a tiny little bit. But if you're continuously running it, you have to to really test it, to that. And also the surface that I'm using here is staying on this wood platform here, and is also affecting the temperature of, if you are mounting it somewhere else, and it's completely in air here. If you're putting it into a box, it will heat up that box, and in turn, that heated box inside will heat up even more this heating element, and the temperature will rise even more when it's inside the box. So that's the thing. You have to test everything until you reach the optimal temperature versus watts, that you like, and that is optimal. That's it. And thank you very much for watching. Thank you very much for understanding this experiment. Leave a like there and say thank you to your favorite artist reference, Mr. Q12. Bye bye. To the next experiments. Bye bye.